of file organization, or how the data has been organized in that particular storage. So a file is a sequence of records stored in a binary format. At this level, I would want to assume that everyone understands that the data stored in a disk primarily is actually realized in form of binaries or 0 and 1. Then when I'm defining a file, a sequence of records stored in binary formats, that can recall in your mind that any data represented in a computer is in terms of ones and zeros. So a disk drive is formatted into several blocks that can store records, so that file records are mapped on those disk blocks. We'll later see how this mapping works. So there are a number of file organization methods that we have. We have heap file, sequential file system, hash file systems, and clustered file systems. And there's the names independently suggest when I say heap file, I mean those files which are just put in, not considering any order. Sequential file following a certain order, hash file based on hash value, and clustered file on grouping. So heap file organization is a type of files organized in such a way that the memory area is clustered and the file does not have any ordering or sequencing or no indexing on its own. So that for us to be able to access this file, the file records can be only accessed with the help. Yes, is there any? Yes, we are talking about a heap file, and we are saying it is the responsibility of the operating system in that regard to manage these records, since the records do not follow any ordering, sequencing, or indexing. So OS allocates memory areas to that file without any accounting details or logging to be able to create a certain order or sequence. You know, once it is logged, at least the logs can be able to follow a certain sequence. So just the OS allocate memory area to that file without any accounting to follow it. There is sequential file organization. The second one, as the name suggests, sequential. It means that this is a file which actually is based on ordering. So in sequential file, records are placed in some sequential order based on unique key field or search key. So the sequential file organization is based on unique key field or search key. So it is not possible to store all the records sequentially in a physical form. Considering on the voluminous nature of data in a database, we would say that it is not possible to order all data entering into a database in following sequential ordering. But it's just good to appreciate the different types of file organizations. The heap file, which you are saying no ordering, or it is not based on any ordering, sequencing, or indexing. The other one is sequential, which is based on unique key or search key. The other one is hash file organization, which is based on hash function. And you realize that this hash function, as you know, is a computational, it's a mathematical computation function. So as soon as you're storing data, it is based on this particular computation known as hash function. So there is hash function computation on some fields of the records. So, and the output of the hash function determines the location of data or where the data has been stored in the disk. So as soon as any new data is generated, then an hash value is computed, and that hash value dictates where that data will be stored. The fourth one is clustered file organization, which clustered file is not considered good for large database. And in this mechanism, related records from one or more relations are kept in the same disk. So, which eventually, the ordering of records as it is in a clustered file is grouping. So there is no use of primary key or search key as you had seen in sequential ordering. Remember, in sequential ordering, we said it is based on unique key or search key when we talk about sequential ordering. So this clustered ordering is just grouping, so that you are grouping related data in same blocks. So it is not based on primary key or search key. So having appreciated the different file organization methods, you also need to know on file operations that you can perform on a file or a database file. In that regard, there are two main operations: update and retrieve operations. As you know, update changes the data values, and you can use insert, delete, or update the way you had seen in DDL, DML, and DCL statements. So retrieval operations, on the other hand, do not alter the data, but retrieve them after optional conditional filtering. So in both of these operations, update and delete, selection plays a significant role. Yes, we are receiving some background interference, please. So other than creation and deletion of files, there could be several operations which can be done on files, apart from what we are saying here on creation and deletion. So we have open, locate, read, and write. So we can be able to read on the other operations that can be done, so that you know what we mean by open, what is locate. When I talk about locate, it's very important. It uses a pointer to make reference, which tells the current position where data is read or written. So pointer can be adjusted accordingly using the find seek operation, and it can be move forward or backward. Take note of locate. These are normal, read, write, and even close. When I say close, then it means the most important operation from the operating system point of view. And when one requests close a file, then we are saying it removes all locks if in a shared mode, and saves the data if altered to a secondary storage media, and releases all the buffers and file handlers associated with the file, or the locks, or it releases the locks so that the other processes can continue. So kindly understand the file operations: update, delete. What situation can we say it's open, locate, read, write, close, like that. So having seen file organization, there's also a very important topic on storage system. And maybe just to go as an overview, because this diagram is very familiar to you. When I talk about primary, secondary, and tertiary memory, you know what we mean here. When I say primary memory, you know I'm talking about the CPU. Secondary memory, I'm talking about the hard disk. And then tertiary is for purposes now of storing huge volume of data. So considering speed of access, you realize that primary memory is one of the memories normalities where you have the cache memory, which is directly accessible to the primary memory. And the speed at which the CPU accesses this kind of memories is that the speed is faster, considering it can access the primary memory very fast, followed by secondary memory, and followed by the tertiary memory. So speed is going upwards, high speed of access, followed by these ones. In terms of storage capacity, again, it is opposite, such that the higher the speed at which a memory can be accessed, then it means the smaller the capacity. Like tertiary memory, it means very, voluminous, and it means the larger the volume, the slower the speed of access. So it's just good to appreciate the storage system, considering also the memory hierarchy, which you know, we're talking about issues of cache memory, key issues of both CPU. Maybe just to mention, CPU has direct access to main memory, which you know, as well as inbuilt registers. And access time of main memory is obviously less than the CPU speed. So to minimize speed mismatch, cache memory is introduced. And you know that cache memory is a very high speed semiconductor memory, which is actually storing data that is currently being processed by the CPU. Our interest so much comes to this magnetic disk and redundant array of independent disk. It's a new concept you might be coming across. So magnetic disks as it is, I want just to say that the way data is stored in a storage device or an hard disk, when you save data in a database, actually that data goes again to your hard disk. And the way it is represented is in form of binary or zeros and ones. So once you save the data, these disks work in a way that the hard disk contains metal disk coated with magnetizable materials. So these disks are placed vertically on a spindle. Spindle is like a reader, something which is rotating so that it can be able to do read and write. So a read-write head moves in between the disks and is used to magnetize or demagnetize the spot under it. So when I talk about magnetizing, I mean introducing an instruction like 1 or a binary 1. Demagnetization means 0 on that spot. So a magnetized spot can be recognized as 0 or 1. So that those ones are the instruction when I magnetize or demagnetize. So hard disks are formatted in well-defined order to store data effectively. So hard disks has many concentric circles on it called tracks. So that subdivision of the hard disk or the hard drive in that regard into sections, so that those sections are now the storage spaces, is known as the tracks. So every track is divided into sectors, and a sector on an hard disk stores 512 bytes of data. That subsection or subdivision of a track or space is what we would take as 512 bytes of data that can be stored by every single track. Remember, I've said it is like the service of the hard disk is subdivisioned into sections, and those sections are what we would refer as tracks, and those storage spaces are 512 bytes. Now, a new concept is known as redundant array of independent disk, which I want you to take notes, or what we say RAID. So RAID is a technology to connect multiple secondary storage devices and use them as a single storage media. So being able to join several secondary storage devices and use them as a single storage device or media is known as redundant array of independent disk, or what we say RAID technology. RAID technology, or this combination of independent disks so that it appears as one, is realized in actually six levels, 5 main levels, and there's also one extra one, which is 6. So normally this redundant array of independent disk starts from RAID 0 to RAID 6. So the different technologies of connecting the independent disk into one single storage media to be viewed as one single storage media starts from RAID 0 to RAID 6. So let's see RAID 0 and be very keen on this, so that once we are moving up to RAID 6, we still have the concept. But underlying concept is that we are just combining the storage so that it can be read as one storage. Remember, in conventional world, we have enormous data. Like, for example, when we are working in a data center, you realize that we have voluminous data, which again, you should be able to retrieve as one data. For example, you are retrieving data from YouTube. Remember, there are different storage locations which need to be synchronized to appear as one. This is where now this technology known as RAID comes in. So RAID 0, in this level, a striped array of disk is implemented. So the data is broken into blocks and the blocks are distributed among the disk. Get the concept that we are talking about striping, like an arrangement in that regard, is implemented on the disk and the data is broken into blocks where each block is distributed among the disks. So each of these disks receives a block of data to read and write in parallel. So RAID 0 actually, as it is, works in parallel so that each of these stripes or blocks receives a block of data to read and write. So it enhances speed and performance of storage device. Now, something else to note about this RAID 0 is that there is no parity and backup in level 0. So if we would be thinking about a situation where we have highly sensitive data or volatile data in that regard, sometimes I would regard that this might not be a very good approach using RAID 0 because of lack of backup or a computation based on parity bit. So this, you have a RAID controller so that it connects the other disks. This is how the storage has been implemented. So that this is, at the end of the day, using this RAID 0 all the way to RAID 6, what connects it to your machine or what connects to your computer in that regard is the RAID control. This is what connects to the other independent disks. Now we have redundant array of independent disk 1, or what we say RAID 1. RAID 1 uses mirroring technique. And be comparing RAID 0, RAID 1 like that as we go sequentially. So RAID 1 uses mirroring technique. That's the key concept brought about in RAID 1, mirroring technique. When data is sent to RAID controller here from your computer, it sends a copy of data to all the disks in the array. So RAID level 1 is also called mirroring, considering the technique that is applied in RAID 1 and provide 100% redundancy in case of failure. Why? The technology underlying the mirroring technique, so that in this disk AB, you have a similar disk AB being generated, which is actually what we're talking about, mirroring technology, copy of exactly the other storage. RAID 2 records error correction codes, or what we say ECC codes, using arming distance from its data. You see, ECC AX block, ECC BX block. So error correction codes or CCC using arming distance for data, which is striped on the different disks. Just like level 0, each data bit in a word is recorded on a separate disk, and ECC codes of the data are stored in the different set disks, so that each and every disk has its own associated ECC code, and which we have said these ECC codes are generated using or considering arming distance. So due to its complex structure and high cost, RAID 0 is not commercially available, considering this technology which uses ECC. So get the key concept being applied. RAID 1, we talked about mirroring. RAID 2, we are now introducing ECC using arming distance. RAID 3 stripes the data onto multiple blocks. You see, we are able to put data into multiple blocks or realize data into multiple blocks. The parity bit generated for the data word is stored on a different disk. You see, this is for purposes of in case there is a failure in that regard, then we can, out of this parity that has been generated by the individual data, we can be able to retrieve. So RAID 3 stripes data on multiple disks, and the parity bit generated for the data is stored on different disks. These techniques makes it to overcome single disk failures. Just there's a risk of failure of one disk out of this parity parity block that has been generated, we can be able to retrieve data considering this parity generator. So you can see as we move ahead that we came from RAID 2, which was using ECC. Now RAID 3, we are talking about introduction of parity bits or parity generators. Now RAID 4, an entire block of data is written onto the data disks, and then the parity is generated and stored on a different disk, still similar to that. But note that level 3 uses byte level striping, very important. Byte level, this one uses block level. So both 3 and level 4 require at least 3 disks to be implemented or to implement RAID. Remember, the third disk is the one which actually holds the parity. But now, remember I said 3 and 4, both of them require 1 extra block for purposes of storing the parity. But now RAID 3 uses byte level striping, whereas RAID 4 uses block level striping. That's what differentiates 3 and 4. Now let's move to RAID 5. Redundant array of independent disk 5 writes all the data blocks on different disks, but the parity bits generated for data block stripes are distributed among all the data disks rather than storing them on a different dedicated disk. So you can see in RAID 3, we have an independent parity block here. RAID 4, an independent block for parity. But now in RAID 5, we are talking about distributing the parity bit among or within each of the block individually. RAID 6 is an extension of 5. 2 independent parties are generated and stored in distributed versions among the multiple disks. So 2 parties provide additional fault tolerance. So this level requires at least 4 disks to implement RAID. But taking note of 6, we are now talking about ECC code, queue, and XOR parity. Remember what we talk about in XORing. And, the same concept applies, which coming in from logics or logic gates. The same concept was discussed in XORing the data. So this one tries to XOR the same data and store in the different independent disks. So we are saying the key difference in 5 and 6 is that RAID 6 is just a small extension of 5, but 2 independent parties are generated and stored in a distributed version among multiple disks. So 2 parties provide additional fault tolerance. So this level requires at least 4 disks to implement RAID. But you can see this one requires 3 disks where the parity bit has been distributed individually on the independent disks. So I just wanted you to be able to understand in an overview the storage system and be able to appreciate this technology known as redundant array of independent disks, so that when you come across RAID, you just know that these ones are disks which are implemented, independent disks which are implemented in parallel, but at the end of the day, they serve as one disk. So very important. So that is a storage system. Maybe before I move, I want to get questions before I move out of this technology known as RAID. If we are still together, let me know. Indexing is a technology where we want to be able to improve on database performance so that we are able to optimize such operations and or queries in that regard. When we want to improve performance on our queries, then we do indexing. So as you know, data is stored in form of records. So every record has an associated key field, which helps it in recognizing or unique recognition, like the primary key, as we've been using it before. So indexing is a data structure technique to effectively retrieve records from a database file based on some attributes on which the indexing has been done. I can do indexing based on ID. I can suggest to do indexing based on age, for example. So, and as it is suggested, you can see index is just like a reference made from a table of contents in your textbook, so that I can easily locate a particular section of my book, considering the index applied from the table of contents. So following the table of contents or index at the back of your book, it can easily refer you to that specific resource where it is found within a book. Remember, a database is a very large storage consisting of enormous voluminous data. So indexing becomes very important, especially when the database is growing, so that you can be able to properly optimize our queries. So indexing is defined based on indexing attributes. So it can be of primary index, secondary index, or clustering index. So primary index is defined on an ordered data file. And normally this ordered data file is the key field, which you know, the primary key. That is what we would regard as primary index. So in general, the primary key is actually the primary index of your relation, which you know, just to remind you. Secondary index may be generated from a field, which is a candidate key and has a unique key in every record, or a non-key with duplicate values. So this similarly works like just the way you would reference a foreign key. So that we can say a key can be generated from a field which is a candidate key and has a unique value in every record. Remember, we said foreign key is like a primary key on the other tables. So clustering index is defined on an ordered data file. So the data file is ordered on a non-key field. So any data file ordered on a non-key field, which is not a primary key, can use clustering index. So ordering is of two types. When we want to order data and organize it based on index, we can do dense indexing or sparse indexing. So we can be able to see an overview of a dense index, sparse index, and multi-level index. The others like P+3s. So dense index is an index record. There's an index record for every search value in a database, so that this makes searching faster, but requires more space to store index records. So index contain search key value and a pointer to the actual record on the disk, so that we map, so that, for example, we use this China as the index, then it should be able to map to the other records for China, Canada, map to the other records for, that is what we mean by dense index. So this is where an index record for every search key value in the database. So this makes searching faster, but requires more space. You cannot define each and every index for individual search key. Sparse index is index records. Index records are not created for every search key, which you had seen in dense index, which it was creating a record, or every record has its own independent search key. So but for a sparse index, every search key, there is no such key individually for every record. So an index record here contains a search key and an actual pointer to the data on the disk. So to search a record, we first proceed by index record and reach at the actual location of the data where it is stored. So if the data we are looking for is not where we directly reach by following the index, then the system starts sequential search until the desired data is found, so that it is moving like that. up and downs, trying to point or search that particular which matches that index. So it is be able to be searching all through like that, going through again. China, then it searches like that until it meets where there is China. Russia scrolls like that until it finds where there is Russia, like that. That's sparse index, not defined based on any specific search. Multi-level index is an index record comprise such values and data pointers. Multi-level index is stored on the disk along with actual database files. So you have the multi-level index together with the actual database files. So as the size of the database grows, therefore these indexes again are growing considering the size of the database. That's why we would say multi-level index. So this index grows, it is growing considering the size of data in the database. So there is an immense need to keep the index records in a main memory so as to speed these search operations. It might not be very effective if you cannot be able to put it somewhere which can be able to speed the search process. So you need to place this index. For example, this multi-level index is realized that we have outer index, which are now the ones which is directly accessible, then followed by the inner index, which now directly connects to the individual data blocks. So you will be growing these indexes, considering the data blocks to be connected. So the inner index will be growing considering the data blocks, so that outer index are associated to each individual inner index. So in this sense, it is able to improve the speed of search. Remember, it is not possible to store all these indexes in a primary memory or a high-speed memory. So that's why we are saying it's good just to keep these outer indexes in such a way that it gets easily to map to the other inner indexes, which maps to the data blocks. There is P+3s. So P+3 is a balanced binary search tree following a multi-level index format, which you can see this multi-level index format, how it looks like. It's not far from how you can see in this diagrammatic representation of P+3s. But now the P+3s works in a system of leaf nodes, so that we are like expanding the leaf nodes. So P+3 ensures that all leaf nodes remain at same height and balanced at the same level, maintained at the same level. Remember this one we're saying it is growing, you can grow the indexes such that index grows considering the data blocks. But P+3 ensures that all leaf nodes remain on same height. Additionally, the leaf nodes are linked using linked lists. Therefore, a P+3 can support random access as well as sequential access. That's what makes P+3 quite different from multi-level index, is that in P+3, we are talking about random access and sequential access being able to be achieved in a random access. Remember, the data is scoped at a similar level, so that we don't have, like in index, we have levels of indexes. But this one is straight to leaf nodes. So those ones are stories about leaf nodes, tree deletion, how you remove a leaf node like that. So you need to read on leaf nodes, P+3 insertion, P+3 deletion. So that's an overview about index. The other important thing is hashing. So maybe I wouldn't want to proceed. We are able to appreciate how we create an SQL table, so that this is an SQL that creates a table which has these fields: ID, name, age, address, salary, and a primary key. You know this is familiar. Now you are told to create an index, and this index should be based, for example, on your age. Then the relevant index based on age, how you create is that you issue the statement, create the syntax is that create then followed by index keyword, then the individual field where you want to base your search on. Remember, I said indexing is a means to be able to optimize the performance of your queries so that you can easily do querying. So on this particular table we have created, I can create an index based on age so that I can say IDX, which is index hyphen age. So it will be based on retrieving data based on this particular value. So you create index IDX age on customers into brackets age. I hope you get the syntax. So it will be pulling data or sending queries considering this field on age. So I hope you have seen one scenario. So you can do that as an assignment based on the table we previously created in our class. I think we have a customers table. Can you now create an index based on that customers table we created in class? Will that be in order? So that you can be able to appreciate the functioning of index.